All right, hello, welcome back. Today's topic, we're going to talk about this concept called principal component analysis. This is a Northeastern University course. It's Northeastern University, only one of the best school in the world. Anyways, so the prerequisite, make sure you go over the prerequisite topics. You should understand all of these topics before you take this lecture. If you don't, you want to go and review them. Otherwise, you're not going to get the most benefit out of this class. And these are the topics we're probably going to end up covering today. So let's start. Understanding centering matrix. Well, as one of the prerequisites, hopefully you've done some kind of data centering in the past, right? In many algorithms, it is required for you to center the entire data. So far, I told you that we stack each sample, x1, horizontally into a matrix, right? So this is sample one, sample two. Even though a vector is like this, we turn it horizontal and we stack them when we have whole bunch of data. Now, one of the things we do very often is essentially removing the center, centering the data. And if we have multiple dimensions, so right here, there are 2 dimensions per sample. For each dimension, centering in the if you I assume you learned it, is you basically find the average of each dimension. So for this example, the average will be 4/3, and the average of this would be out of 3 would be 1, right? So 4/3 and 1. So what you do is you take each sample and subtract the average away. So take this sample, subtract it, this one, subtract this, so on and so forth. So every single sample you essentially subtract the average value. And that, as a result, centers the data. Right? So you see, it moves on here. After you subtract the average, this is the center result. And we call the center result X bar, just symbolically, to represent it. Now, just in case there's any confusion why we call it centering, you can picture the data here, right? This is the original data. And the center point of this data will be here. If you remove the center, that's effectively moving the data new center to be 0, 0, right? If there's some kind of shift this way, you've removed all the shift, so you've moved the data to the center. And this is a very, very common machine learning pre-processing step you have to do. So, I mean, finding the average of each dimension and subtracting it away, right? So once you find this, you simply have to repeat subtracting this for every single sample. The idea is not very hard, and by now, hopefully, you've done this before. Now, so this is the standard centering that hopefully you've done. There's a second way to understand centering, and that is called the centering matrix. The centering matrix operates differently in that instead of taking x, like here's your data, and subtracting the center, this is x, minus the mu of x, the center of x, and then you get the result. Here, you take x and you multiply by some kind of matrix, and it will give you the equivalent. It will give you the equivalent x bar. So the interesting thing is, well, in that case, what is the centering matrix? Well, it turns out you're doing exactly the same thing. So let's say we have the data x here. This is original data, and there are d dimensions, right? D dimensions. So this is the first sample, and so this is denoting the first sample, first dimension, first sample, second dimension. So that's how we're going to denote this. So this right here is one sample. So when we're removing the center, remember what I just told you. We take each dimension, find the average, right? So if you want to find the center point here, it's equivalent to taking this dimension, this entire column, and if you multiply by a 1 vector, so all these are 1s. So if you do a dot product here, then that's equivalent to adding them together. And dividing by n will give you the average. So this, you add up all them, divided by n. So this operation results in one number, which is the average of this. Now you can do this within the matrix, one operation per column, and you do this for every single column. You can imagine the result here is this is the average value for column 1. This is the average value for column 2. This is the average value for column D. So if you officially have found the average value through this operation, right? This is within a matrix. So inside a matrix, each element is actually an operation, which results in a number. Now, over here, this is 1 over n. It's a constant. You can pull a constant out of the matrix. This right here is a vector. You can also pull them out because they're the same, right? They're exactly the same. So you pull both of them out. So now you have 1 over n, and here is the one vector we pulled it out. After we pulled it out, the residual portion, guess what? It's just the original matrix X. This means that if you want to find the center point, it's actually just x times the 1 vector divided by n, which is this. The centering data. So data here, right, this is equal to this. This vector right here is equivalent to just taking the matrix, the original matrix itself, multiplied by 1. This is a vector of 1s, of course, transposed, divided by n. So this is the first conclusion, that you can find the center point by multiplying the original x by 1 and divide by n. Okay. Now, remember, once you find the center point, what do we do? Well, once we found the center point, what we did is we made multiple copies of it. So this was the center, and then we made a copy for every single sample. So we need to make n copies, right? So how do you make copies with vectors, right? Well, making copies with vectors is actually not that hard, right? Let's say we have this right here. So let's say the center is equal to 1, 2, right? So this is the center, which is these points, only 2 dimension. How do we make copies? Well, copies is really, really easy. You just multiply by a vector of 1, right? If you multiply vectors of 2 1s, you make 2 copies. Notice how the outer product here results in 1, 2, 1, 2. So you made 2 copies. All right, what if we have 3, right? So we had 1, 2, 3. So this obviously, then you make 3 copies. So 1, 2, 1, 2, 1, 2. So if you want n copies, all you have to do is multiply a vector of size n. So we know at this point how to find the center, which was x times this 1 vector transpose divided by n. And now if we multiply this by another 1 vector, right? Remember 1, 1, 1, 1, 1. Well, what is the 1 vector? It's this again. So if we have the 1 vector, this will essentially make all the copies for you, right? So over here, this is exactly what happened. Like, if you are able to make multiple copies, that's equivalent to taking your center, right? These are the centers, make copies by them. And therefore, if we're trying to find the x, that's equivalent to x subtracting multiple copies of the center, right? And the multiple copy of the center is equivalent to 1 single center made multiple copy. Okay, so this is the center matrix is therefore x, which is here, subtract 1, which is here, multiply by however we got the center in the first place, which was x times 1 transpose and divide by n. Okay. Now, 1 over n is a constant. You can move constants anywhere you want between multiplication of vectors. So I'm going to move this out. Right? I move this out. So if you move that out, then x bar is equal to x minus 1 over n, 1, 1, transpose x. So this is a vector of 1. and this right here is a vector of 1s, like this. Well, if you put them together, right, what happens? This is a vector of 1, and you're making copies of vectors of 1. Therefore, it becomes a matrix of 1s. Right? So this right here is a matrix of 1s. So that's how we got this. I moved the 1 over n outside, and this is just a matrix of 1. And the last operation, notice how this is x, so we can pull them out. So after you pull them out, this becomes identity. Notice how if you have x times the identity, then and then x times this, it's equivalent to this expression here. Now, this means that if we have the original data x and we multiply it by some matrix, it could give us the equivalent of centering the matrix, right? And this matrix turns out to be this right here. This is the centering matrix, which this is the identity. Subtract 1 over n times the matrix of 1s. Okay, so that is the definition of centering. So by multiplying a matrix, you could equivalently obtain the same as like subtracting away from the center. So first, you need to convince yourself of this fact. So if this is a matrix here, and with this matrix, you want to, if we already calculate that the average is this. So if you subtract the average, you will get this. Now, equivalently, if you take your original matrix X and multiply by the centering matrix, you should get exactly the same thing because they are mathematically equivalent. So, you want to pause the video and see if you can do this. See that if you take the matrix X, multiply by the centering matrix, you should get equivalent to just subtracting the average away. Okay, so that's the idea of centering matrix. All right, so pause the video. Make sure you do this. Like, if you don't follow through with these exercises, then the later concept gets harder and harder to understand. So you do want to pause the video and give this a try. Okay, so properties of centering matrix. Well, one of the property is that the centering matrix is equal to its transpose. Okay. The second one is that the centering matrix multiplied by itself is the centering matrix. So the fact that is equal to its transpose, you can just see it. You can just you can write this out and you'll see that it is the same. The fact that if you have x and you center the data, right? So if you have data here, you centered it. And if you try to center it again, it's just going to stay here. Therefore, centering twice is equivalent to centering once. In fact, centering as many times, once you're stuck in the center, you're just always going to be stuck at the center. So it doesn't matter how many C's you multiply, that's equivalent to just one centering. Okay, what I want you to do now is pause the video again, try these two properties. So this right here is the centering matrix. See yourself that the centering matrix, if you take the transpose, is going to be identical. Second, see that if you multiply two centering, in fact, 3 or 4 centering matrices together, it's equivalent to itself. Okay, pause the video, give this a try. We're going to move on to the next section. From summation to vector multiplication. So this is the next building block we need. Okay. From summation to vector multiplication. In machine learning and data science, we often need to perform various summations. These summations could be done with vector multiplication. So let's say we have a bunch of x values. Here's x, and this is essentially a vector of numbers. So this is a vector. So this is a vector. This is another vector, right? So you have two vectors. Now, we very often need to perform operations that is summation. So let's take this very simple one. It's just x for every single one of these, right? We are basically taking the square and summing it up. I want you to notice this is equivalent to taking the inner product, basically the dot product between x vector itself. Therefore, notice how this multiplied by this adds this multiplied by this adds, which is x1 square, x2 square. So this summation could be easily done by doing x transpose x, like such. Okay. Now, this idea extends to itself if it's x and y. So here's x1, y1. So notice how when you multiply it's y1 times x1, y2 times x2, y3 x3, right? So this summation can be written as x transpose y. And this could extend. So let's say we are centering. This is x minus the center square. So notice how over here is just x, but over here is x minus the center. Well, this right here is x1 minus center, x2 minus center, x3 minus center, times x1 minus center. So notice how the first element here multiplied by this, that's how we got the square. And then adds to the second element, square, so on and so forth. Well, what is this right here? Right? What is x minus the center, right? The center point. Well, we just learned this. This right here is the vector x multiplied by c, right? This is equivalent to centering. Like before, we had a whole matrix, right? But right now, we just have one column of it instead of multiple columns. So this is just one vector x. If you multiply by c, that's equivalent to taking this and centering it, right? So this right here is the transpose of this. So it's x times c times x times c transpose. So from here, this expression here can be simplified into this here. Now, if I move the transpose inside, so it's x transpose c transpose times cx. Well, I told you c transpose is equal to c. Therefore, this is the same. And I also told you that c times c is just equal to c. Therefore, the final result is just 1c. So you can essentially write a for loop in your program that basically loops through every one of these. But a much easier way would be simply take the vectors, multiply by the centering matrix. You can do this in one line. This is actually really, really easy. So harder to program, easier to program. Similar idea extends. Right here is x minus x mean. What if you have x times x mean instead of square? You have x times x mean times y mean. Well, that we can extend this idea further, where you have x1 times x mean, y1 times y mean. Notice how you multiply them together, and then we add it to the next one, x2, y2, right? And then we can apply the center idea again. This is just c times y. And this one is the same. It's c times x transpose. Just like the idea from right here. They're the same idea. And of course, we simplify. So you can really, really simplify this expression basically using this notation. It's just the x vector itself, right? X vector times centering and then times y, right? And this, being able to simplify this large and complicated summation into just a basic matrix multiplication will make your life a lot easier. So you want to really pause the video and go over this section and understand what is going on. How is it that we can convert these summation into a vector multiplication? And vector multiplication makes your life so much easier. Okay, so pause the video, study this slide. All right, so in the previous lectures, you have hopefully gone through the concept of variance and covariance. Well, guess what? The concept of variance, this right here, looks very similar to what we just did, right? Well, what we just did is, here's the variance. In fact, the concept of covariance looks very similar. Therefore, if you were to piggyback off everything we learned, then the concept of variance can essentially, this part, right? We just learned this is equal to x transpose cx, and then 1 over n. So you can calculate variance this way much easier. than if you try to like do this one at a time, which is would not be fun. All right, you don't want to calculate this n times. You just want to do a single matrix vector multiplication. Similarly here, right? This is 1 over n, so you have 1 over n x transpose c y, right? Because this is the y. So the idea really extends. So the concept of covariance can be calculated easily for via like vector-vector multiplication, and the concept of variance can be calculated easily via vector-vector multiplication. Okay, so converting summation into these will make your life a lot easier. Will make your life a lot easier. Now, I want you to take a moment, basically, see if you can do it yourself. Try to step through the ideas that we just stepped through and see that if you can somehow arrive to the conclusion where the variance is simply 1 over n, c trans, x transpose cx, right? And then see if you can come to the conclusion here. This is 1 over n, x transpose cy. All right, pause the video. Like it's crucial that you're able to do this in order to understand the next step. So pause the video, really pause it, really go through the slides, and then make sure you can do. You're convinced of this. Okay, a lot of this is a lot of learning. You're basically like learning something new about the world, and but they're just facts. Just learning about the facts is very different from you experiencing the facts. If you go and actually try to do it yourself, and then it happens to match what you were taught, then you are convinced that that is the reality. Otherwise, you're never going to remember it. So again, pause and try to do it. All right, so I wrote the solution out for you. So if and then and I also wrote the code, so you can see that this right here basically calls the numpy. This calls the numpy variance, and I got a result. And if I had used this c c x transpose dot c dot x, right? That was x transpose c x divided by 5, which was the number of samples. Notice how the result is basically the same. Okay, so so they're equivalent. All right, so now you know how to find variance and covariance in both, like its definition, right? You know the definition, right? Which variance is the average distance from the center, right? Average distance from the center. Covariance tells you the dependency, right? If a sample is more likely to be above the average, then the y is also more likely to be above the average. Okay, so these two are the definition, and you now know how to essentially rewrite them in a simpler, more compact form of vector-vector multiplication. All right, so performing multiple projections. So that's like right now, everything we're learning are building blocks, and you need to understand a lot of building blocks. It's kind of like a point here. Well, actually, no, I'm not going to get into that. I was going to talk about span. If you only understand certain things, you're never going to be able to span this point. Anyways, I'll skip that for a different lecture. Anyways, performing multiple projections. So this is the next building block you're going to need. So we previously learned the concept of projection. So at this point, it's assumed that you know projection. If you don't know projection, go to a previous lecture. Watch your previous lecture first. You must know projection to understand PCA. All right. So if you have a data point here and you want to project this, the idea of projection is if there's a sun and you're casting a shadow and V is the surface, basically where at that point V, which is SI here, is this point. What is that point where the shadow thresholds the shadow and the light? So this part will be bright, this part will be dark, right? So what is that threshold point? So this is kind of like the idea of projection. right? And and to do projection, we need to first find a normalized vector v hat. So this is v, and what we normally do is we find this v hat. In order to find this point, it's essentially v hat is a length of one, right? So if this is length of one, how many v hats do we multiply? We multiply by something so that this extends to reach si. So you have a vector and you're stretching it by alpha, right? So the idea is if you want to know this point, you need to simply find v hat, which is how the unit vector, and then you need to find out how much you stretch it to reach the point you need. So finding a unit vector, hopefully you know already unit vector. I should probably add that into a prerequisite. I didn't write that as a prerequisite. Give me 1 second. So v hat as a prereq. V hat as a prereq. Okay, so this is so you need to know like how to find the normalized version of vector, which I hope you do know. And then after that, you need to know how to find alpha, right? Well, alpha is really easy. Alpha times v hat. Alpha is simply equal to v hat times xi transpose. So if you have this is the vector you're doing the projection. You do a dot product between them, and that's your alpha. Now I'm going to skip the reason. It's got to do with the fact that the definition of a cosine. But yeah, like for now, don't worry about the geometric reason why this happens. Maybe I'll post a separate video about that. But you just need to remember if you want to find the alpha value, you basically dot the v hat. Normally, notice this is v hat, not v. Okay, this is this one, not this one. So you dot them together, and you get the alpha value. And the alpha value, then alpha I times v hat will essentially stretch it just enough to give you the point si. So you can get this si, you can get this point si by finding both this and this. And we just quickly went over how to do that, right? So we previously learned how to find alpha I, right? Okay, so now this is just projecting one point. But in machine learning, you don't just deal with one point. Very often you need to deal with a lot of points, lots and lots of points, right? You need to project multiple points. So in this particular example, now you have lots more points. I mean, 3 is not lots more, but like 3 will get the point through. So now you need like S1, S2, S3, right? So we can simultaneously find every one of them because previously it's just V times X1. But if you simply stack them into a matrix, which this together is just the X matrix, if you just multiply V by this matrix, notice how when you multiply this, that gives you alpha 1. You do it again, alpha 2. You do it again, alpha 3, right? So you multiply them each time, and the result is simply the alpha. So you know all the alpha values with single operation, which is x v hat. Well, notice that the points x1, x2 originally reside in 2D. These points are in 2D. However, once you do the projection, all these points now, the point after, they reside in a 1D space, which is just V. They reside right here, right? So they now live in 1D. I mean, of course, you can picture this 1D in 2D space, but in reality, you only really need one dimension to represent each point, right? You only need one number to represent them. So after projection, all the points live along a 1D line, which is V. So after projection, they all live on V. Therefore, each point can now be represented by a single value. This is a key. You don't need, once you know they live here, you don't really need the vector anymore. You just need to know how far it is. So this is alpha 2, this is alpha 1, this is alpha 3. So just by knowing alpha 1, 2, 3, you know where this point is. Okay, a value that represents the new location of xi all along the v-axis. So you assume this v-axis is the alpha value. So as long as you know the alpha value, like previously, we needed to multiply alpha by v hat in order to get this point. So if we multiply by v hat, that implies that we're still in this 2D space. But if we take v hat for granted, that we just know it's going to be on v hat, then we only care about the coordinate. How long along v hat, how far along v hat is it stretching for this point? So, if you are willing to just assume that it's now 1D and it's along v hat, and just get rid of the v hat. So all you really need is the alpha value in order to tell you the location. Okay, so alpha value is good enough after you've projected data. Okay, so xi, you can kind of picture these are the old coordinates. All right, now if you assume x v hat as the new axis, then alpha I is the new coordinate. So all you really need is the alpha I. So you can kind of picture this. So previously, these points in 2D, but once you project them onto 1D, you can picture this as the new x-axis, and this is the new y. This is the original. So if this is the new x-axis, then the points would be alpha 2, 0, right? Alpha 1, 0. This would be alpha 3, 0, right? So you don't need these values. You only care about the alpha value because just one dimension will represent the data. Okay. Therefore, remember what I told you. You can get all the alpha values. You take x, you just multiply each one of them, and that gives you the alpha values. And these also give you the new coordinate, the new basically point, right, after projection along the v hat. So this is a very important equation. Basically, v hat, the normalized version of v, multiplied by x, is how you get the new location. Right? Is how you get the new location along this new coordinate system. Okay, if I like you, this right at this point, these concepts are really important. You need to once again go over them a couple times until you feel really comfortable, and you understand that particularly this equation. Okay, because now we're going to move on to finally learn the principal component analysis. Okay, so PCA. Right. PCA is a machine learning algorithm. And the idea of PCA is very often we have big data, and big data consists of many dimensions, like a million, 100, 1,000, lots of dimensions. But having lots of dimensions, a lot of it could be noise, and it could be really hard to handle. So given so many dimensions, maybe we don't need all of them. Maybe we can figure out like dimensions or combination of dimensions that will be very helpful. We keep and we get rid of the rest of them. Okay, so PCA is an algorithm that reduces the dimension of the data by projecting the original data onto the most important dimensions. So you can imagine the data has certain dimensions. Certain dimensions are more important. Other dimensions are less important. Right? Therefore, if you can just project the data onto the most important dimensions and then removing other dimensions that's less important, then you've essentially removed the dimension appropriately. Okay. So once the dimension is reduced, there's a lot of benefits, right? For one, why is this jumping? 1 second. For one, there's less data to deal with, right? Then if you have less data, then you have less memory to store the data. And then running the algorithm is faster because you have less data. And you're potentially removing the noise out of the system as well, which could give you a much better result. Okay. Remember how we can project multiple points onto a vector. All right. So remember, we take x and we multiply by v hat. So we just did this. And that gives us the alpha, which is the 1D coordinates after projection. So mechanistically, that's what PCA is doing. You find this vector, appropriate vector, such that after you multiply it, notice it's lower dimension. Like here's 4 dimension, here's 1 dimension. So after you project it down to 1 dimension, you find that 1 dimension that's retains the data the best. Okay. Notice how the data go from D, right, D dimension down to 1 dimension after the projection. This is how PCA mechanistically, so you can see it mechanically how it goes from 1 dimension down to 1 dimension. Okay. But here's the question: how does PCA know what V hat is? So we picked this line here, but you can imagine we can pick that one, pick that one, pick this one, pick this one. All you can project the data many ways. How does PCA know which one is the best one? Okay, what is and that goes to the definition of best. What do you mean by best? Right. So by clearly defining the concept of best, right, PCA is able to then pick the appropriate V hat. So how does PCA find V hat? Why is it jumping again? 1 second. Let me jump back. Okay. How does PCA find V hat? Well, let's look at the top figure. Notice that if we use this projection, right, we pick this line, then after the projection, the result looks pretty close to the original data, right? So you didn't lose a lot of information by reducing the dimension. In here, you have 2 dimension. Here, they'll live along 1 dimension. So you've lowered the dimension while retaining the original shape. In contrast, let's pick this line here. Well, if you pick this one, this data really doesn't look like the original one, right? So and therefore this projection did not maintain the original shape and the integrity of the data. So we can from this visually see that certain projections, certain lines that we draw, once we project it along that line, it can do a pretty good job of retaining the original shape, while other projections, it looks vastly different than the original data. Okay? So you can guess if that's the case, if you can reduce the dimension of the data while retaining its original shape, then you lower the data dimension without losing any information. If the data looks basically the same after you do the projection, then you've basically reduced the dimension while retaining the original shape of the data. Right? And that's the goal. You want to retain the original shape of the data. The goal of PCA is to find a projection V hat that maximally retains the original shape. Okay? Original shape. But then the question comes like, okay, we can see that certain projections does a good job, but how do we know, by what benchmark will we use to say that this certain projection does a better job of retaining the shape, right? How will we know that? Well, how does PCA do that? Well, after you project the data onto a line, notice how after you project onto a line, right, it's just an alpha value now. Therefore, we can picture the new axis looks something like this. This is the new axis, right? So you have to rotate your head a little. This is x-axis, and this is the new y-axis. Therefore, you only care about the alpha value. And this range here is the range of the data. Therefore, this right here, you can measure the variance of your data this way. We know how to calculate the variance. So notice the variance for this one is large, whereas the variance for this one is small, right? So variation of the data, you can intuitively see that when the variation is large, that's where the data is mostly residing. When the variation is small, that's where the data that's not changing. That's the direction where the data is not changing very much. and therefore it may not be as important, right? So therefore, small variations coincide with um, less importance to maintain the shape of the data. Large variance after projection coincides with retaining the original shape, right? So obviously, you're going to say this direction is basically the shape, right? This is the shape of. Therefore, you want to retain this shape because this is where the largest variation is. Okay? Now, this is basically the key intuition and insight into PCA. The larger the variation after projection, right? So after you do the projection, this is the variation. Here, after you do the projection, this is the variation. All right. And when I say variation, I'm talking about variance. Like how on average samples, how far on samples are from the center. So if you can preserve, you can find the direction that give you the largest variation. That's the direction that would preserve the shape, original shape, the best. Therefore, once we create the alpha value, the goal is we want to find the v hat such that the variation is maximized. This is the PCA objective. Okay. Once again, remember how we got alpha. Alpha is when we take v times essentially x, and that's alpha is a vector, and we want to find the variance for all the vectors. Therefore, this alpha here is equal to x v hat, right? So we want to find the v hat such that after you do the projection, once again, after you do the projection, you want to maximize the variation. This is the variance after projection. So PCA is trying to find the direction that maximizes the variation after the projection. Okay, so I just showed you that the right here, we're trying to, alpha is after the projection. So we're trying to maximize the variation, okay? Now, we know how the equation for variance, we learned that today. Variance of x is x transpose cx, right? Therefore, variance alpha is alpha transpose c alpha. So, I mean, that's just a change of a symbol. Nothing special there. So you now see we are trying to maximize this. And what do we say alpha was? Well, alpha is v hat times x. So let's plug that into alpha. If we plug that into alpha, then alpha here becomes x v hat, right? And alpha transpose will be v hat x transpose. Okay. So this right here essentially is the equation. Like there's a v hat here. You're trying to find a v hat that's trying to make the variance as large as possible. This is the equation for variance after projection. Okay. Now, at this point, we run into a pretty serious optimization problem because we're trying to find v hat. V hat, if you remember, is a normalized vector, right? Therefore, v hat transpose v hat has to equal to 1. It's saying the length of this is equal to 1. And based on the rules of projection, we need to normalize the v hat. So we are kind of stuck that not only do we want to find v that makes this as large as possible, we need to find a v that happens to have a length of 1. Right? We need that. We need the v to have a length of 1. Now, remember, remember everything we've done with gradient descent. Gradient descent simply go towards the lowest point. It will not care. It will not care or try to ensure that the numbers with v inside the vector v will happen to have exactly length of 1. So there we run into a pretty big problem. The problem is gradient descent doesn't really care. Right? It's just constant. You know the algorithm. It's just trying to go down. It's going down wherever it is, and it's not trying to ensure that the numbers inside the vector meets some kind of criteria. Right? So if we can use gradient descent to essentially maximize this, then what should we be doing? right? So the trick here is to realize that if the norm is equal to 1, it implies that V transpose V equal to 1. And you can see that if you have like a normalized vector multiplied by itself, it will give you 1. So this is a major trick. Therefore, the condition we have is that the V we pick, like the V we pick, because of this condition, this minus 1 should be 0. So this right here is a condition that we would like to meet. So therefore, what we could do is change our objective. Our original objective was to make sure we're trying to find a V hat. Now, let's just try to find any V. But we're adding a constraint. We can't just find any V. We need to find a V such that V transpose V minus 1 is equal to 0. Now, this is a very, very subtle difference. Before, we're trying to find V that happens to have a norm of 1. Now, it's saying we can find any V, but this condition has to be satisfied. All right. I know that seems like a sleight of hand and nothing's really changed because nothing did change. Except mathematically, you can deal with this. This you can deal with. Previously, you can't really deal with that. You can't deal with this one. Now, this right here is called a constraint optimization. When you add a constraint, and we will read this objective as maximizing the objective such that the constraint V transpose V minus 1 has to equals to 0 is satisfied. So this condition has to be satisfied. That's how you would read this optimization problem. Now, there's an entire course on optimization, but I'm going to jump to the solution, the conclusion that you can, in fact, use this for any other constraint. So, given that this is the constraint, this is objective, this is the constraint. We still can't really use gradient descent. Well, then what should we do? Well, in constraint optimization theory, so I don't expect you to know this, I don't expect you to know this already, but I'm going to let you know how we would deal with, right? Whenever you have an equality constraint, it has to equal to something. Well, we first set it to equal to 0. So that's the first thing we do. So if you had V transpose V equal to 1, right, we change it to make sure it's minus 1 equal to 0. Same condition, but the standard is to make sure we set it to be equal to 0. So whenever we have this equality constraint equal to 0, in optimization theory, we add the constraint into the objective. There's a way to add this in to create what we call a Lagrangian. And now, if you took calculus, you would have learned Lagrange multipliers. And if you were to do this, right, it will look like this. This is the constraint. This is the objective. And we will add a constraint right here. And this right here, this number here is called a Lagrange multiplier. Now, this is just a number. Lagrange multiplier. Lambda is just a number. And we don't know what this number is. And this is the standard way. You add the objective, and then you add the constraint. Okay? And then you add a Lagrange multiplier. Now, this works. This works for any constraint, okay? It doesn't have to be this one. If you have another, whatever equation equals to 0, anything, you can always convert it into a Lagrangian. So that's step 1. You convert into Lagrangian. According to the theory, the optimal solution, if you're trying to find the optimal solution of a Lagrangian, so we convert our original objective into a Lagrangian. Once you have it in a Lagrangian, right, the solution is when you take the derivative of this and set it to 0. All right, so remember, if you want a closed form solution, you simply you're trying to find the point where the derivative is equal to 0, or for maximization, right? The derivative is equal to 0. So if you take the Lagrangian's derivative and set it to 0, and then you are solving for v, you solve for v, then your problem is solved. So that's what the optimization theory says. Therefore, let's give it a try. Well, this right here, I can rewrite the 3 matrix. We know what they are. It's just Q. So this right here is just Q. Right, Q. And this right here is equivalent to multiplying identity matrix in the middle. Right. So, and then I multiply this out. So take a second and study how this is equal to this. Right. I just made this part Q, and then I multiply them together, add an identity in the middle, and then I multiply lambda here. Okay, so take a second, make sure you get this. Well, we spent a lot of time this semester learning how to take derivatives of matrices and vectors. So the derivative of this, note that Q is symmetric. Therefore, the derivative of this is 2QV. So now, if you don't remember how to do that, let me make sure I add that to a prerequisite. Matrix calc. Okay. If you don't remember how to do that, make sure you know you can go back and understand how I took the derivative of this. This is also quadratic. In the middle, it's just an identity matrix. So you can take the derivative of quadratic. This is a constant that disappears. So this is the derivative here, and we can set it to 0. Now, if we set this to 0, we can just move this to the other side. And notice that this right here, we end up with a relationship that we have a vector multiplied by Q is equivalent to a vector multiplied by a number. So this vector views Q as a number, right? V multiplied by matrix is equal to V multiplied by number. Now, we spent a lot of time on this matrix, on this relationship. Remember the lecture on soulmates, right? So if you have a matrix, the soulmate of the matrix is V, because V, instead of viewing you as a matrix, right, it views the core, the core of who you are, and only sees the number. Like the vectors. Anyways, if you don't remember that, make sure you go and watch that lecture on how V is the eigenvector is the soulmate of the matrix. So basically, this equation here is the eigenvector and eigenvalue. This is the eigenvector and eigenvalue of Q, and that's it. So solution V. So therefore, this is a definition of eigenvectors of Q. Therefore, what this is saying is that when we are trying to solve this like PCA problem, the solution is simply the eigenvector of Q. If you find the eigenvalue, a vector of Q, that is your V. That's what this is saying. Like, because we set the derivative to 0, right? Once you set the derivative to 0, the only way that this condition could be true is that if V is the eigenvector of Q. Okay. Now, you may remember when we find eigenvectors, when we have worked with eigenvectors, you will know that Q doesn't just give you one eigenvector. It gives you lots and lots of eigenvectors. Therefore, which one should you pick? If you got multiple of them, and we only really need 1 or 2, which one should you pick? Well, to pick them, you need to remember 2 facts about eigenvectors. Fact number 1 is that all eigenvectors are already normalized, right? So that's very helpful, right? Remember, we needed them to be normalized. So this is automatically satisfied just by picking eigenvectors. So we need to remember that V transpose V is equal to 1. The second thing you need to remember is the definition of an eigenvalue eigenvector. Okay, so if you know these 2 things, we can now answer the question of which eigenvector we should pick. And let's pretend we have 2 possible choices of eigenvectors. Choice number 1 has an eigenvalue of 5, and choice number 2 has an eigenvalue of 1. And let's just plug them in. If had we pick choice number 1, V1, well, notice that this right here is the definition. Therefore, this right here is just lambda 1, because this right here is equal to lambda times V. So it's lambda 1 times V1. And lambda 1 is a number, implying that we can move the number out. So now the number is out. And guess what? This right here is V1 times V1. And we know exactly what that is as well. It's just equal to 1. So this is 1. Therefore, the result is 5. That's case number 1, right? Where the eigenvalue, lambda 1, is equal to 5. Now let's pick case number 2. If we pick case number 2, similarly, now you have V2 times Q. Using the definition, this is equal to lambda 2 times V2. Now we can move V2 out. If we move lambda 2 out, and once again, V2 times V2 is equal to 1, resulting in 1. So if our problem is we're trying to maximize this, right? Should we pick the first eigenvector or should we pick the second eigenvector if you're trying to maximize this? That reduces down to which one is bigger, right? So if you pick the eigenvector with eigenvalue that's larger than all other ones. So the largest, the eigenvector with the largest eigenvalue will give you the maximum. And that's how you know how to pick. Right? You know how to pick them based on the largest eigenvalues. Okay? Okay. Now, what if we want to project down to multiple dimensions? Right? So right now we project down to just one line, right? One line. But sometimes you want to project down to 2 dimensions. So from 100, maybe you want to project down to 2 or 3, right? Because if you project onto 1 or 2, maybe you lose too much information and you want to maintain most of them, right? So if you want to project down to multiple of them, then what do? Well, if you pick one eigenvector, then you are going to project down to 1 dimension. If you pick 2 eigenvector, then you're going to project to 2, right? So notice how if you pick 2 eigenvectors, right here, essentially reduce it down to just 2 dimensions. So these 2 are eigenvectors. Okay. So you can see you just have to pick more. And this could be done by changing the original objective to you want to pick the first V1 and V2 such that V1 minus V1 is equal to 0, V2 minus 0 equal to 2. So you can change the objective slightly so that you now have to have 2 of them. And therefore, since we already know what the solution for this one, so if we already pick V1, then to pick V2, we pick the next largest eigenvalue, right? Eigenvector with the largest eigenvalue. So if we do that, so we just pick, if you need 3, then you pick 3 eigenvectors with the 3 largest eigenvalues, okay? In general, if you want to reduce data to Q dimensions, then you just pick Q eigenvectors with the largest eigenvalue. So that's how you know. That's not how you know. Okay, so another question often asked for PCA is, well, we now know how to project down to multiple. So it doesn't have to be 1, even though we use 1 as the example. But extending from 1 to 2 is very easy. But how do we know how many dimensions we should reduce the data down to? So how many should we reduce? So just because we know we can reduce down to multiple dimensions, we don't know what that multiple is, right? How many should we use? Well, this is a very commonly asked question. Like if we have 100 dimensions, how do we know the appropriate dimension we should reduce it down to? Well, let's pretend we do have 100 dimensions. Let's pretend that. Resulting in 100 eigenvectors and eigenvalues. And let's take a look. Let's pretend out of 100 of them, the first one is 5 for eigenvalue. The second largest eigenvalue is 2. the third one is 0.001, and the fourth one is 0, and everything after the fourth, all the way to the 100, are 0. Okay, so these all have eigenvalues of 0. Now let's pretend we reduced it down to 50 dimensions. So we pick 50. If we pick 50, this means we need to do this 50 times. Right? So there are 50 of them. So this implies we pick the larger one, second one, third one, fourth one, fifth one. And if we were to follow what we learned previously, the result of this was 5, right? It will give us 5. The result of the second one is when we pick the second largest one, result in 2. Well, the third one then result in 0.001. But the fourth, all the way to the 50th, are 0. So do we need any of these? No. The answer is no. You don't need them. This kind of tells you that all you need is 3 dimensions, and you will not be able to make this any larger anyways. So the rest of them, from 4 to 50, were unnecessary. In fact, there's an argument to be made that by adding the third one, you're not adding much, right? You're basically not adding very much anyways. So we probably could assume the third one was just noise and get rid of it, right? Just get rid of it. Therefore, in this particular case, I would have just picked 2. So you now know the 2 dimensions simply by looking at the eigenvalues. Okay? This observation tells us that we really didn't need to include 4 to 50 because their contribution was so small, right? Well, not so small, 0. And we could have eliminated 3. Therefore, by looking at the eigenvalues, essentially, we know exactly how to pick which one. Okay? All right, so let's do an example together. Let's say this is a data, right? The key here is to get the Q. Once you know the Q matrix, then it's really easy to solve because the solution is simply the largest eigenvector of Q. So how do we get Q? Well, it's X transpose CX. So we calculate C, right? This is C here. Once we know C, we simply multiply X transpose CX, which give us a matrix, and we now know take the eigenvectors. After we take the eigenvectors, guess what? This one is larger, right? This is a larger eigenvalue. So we pick this one. Notice how if we pick this one, it gives us a really, really nice line here, which then you can project the data onto. So this will go here, right? They will all go onto the line. Okay. All right. So once we have V, so that was the V here, then all we have to do is multiply V by our original data. Let's see. Here's our original data. We multiply V, and then that's our alpha value. And that is the resulting dimension. So it will be as if the new axis is x-axis and y-axis, and these are the new points along this line. Okay? All right, so next. I wrote the code for you over here. There are 2 ways to run PCA. Well, the first way is you just write the code yourself. So notice how it create a centering matrix, and then X transpose C dot X, right? And then if I find the eigenvectors, pick the largest one, we have the solution. Of course, if you are at work and you're learning you can just use sklearn, which allows you to call the command PCA. So the first approach, you write everything yourself. The second approach, you just call PCA. And the component essentially tells you how many dimensions you want to reduce down to, right? And fit transform, so this is your final alpha value. So this is a new location, coordinates, right? So now I want you to practice what we learned today and see if you can essentially find the projection that would make this the most sense. Okay? Hopefully that's good. I will see you in the next lecture.